This is the type of lesson that makes me really love Calc 3 because it just pays off to remember things throughout the whole year. Like here where we're talking about surface area, it comes from arc length. If you remember with me, right, when we're measuring arc length, we would take the infinitesimal measure between these two places. I would see dx, I would see dy, and that change, dx squared plus dy squared, as x changes, this is dx, dx, dy, dx gives me this length. And if I integrate it over the whole surface, or through the whole curve, from a to b, I would have the total length of the curve. Well, now I'm going to do the same thing, but I'm going to take little areas. And I'm going to add up all of those little areas across the surface to then get the surface area. So you can kind of see this projection here, where let's just focus in on this one little guy to understand what's happening here. See, this surface has some curvature to it. So I've got a little, curvature to this guy. Not a perfect area. Not a perfect area by any means. But it's not quite a rectangle, but it is another shape that we know. And so what I'm going to do is I'm going to call this side vector A. And I'm going to call this side vector B. And guess what? I kind of know the measures of A and B. Like here, A is delta x. And B is delta y. Just that kind of arbitrary change. But again, this thing has curvature. It has a third dimension. I can't just say, oh yeah, it's just, this vector is just a single directional, like where A would be delta xi. That's not quite accurate because there is a change in z. Well, what would I call a change in z with respect to x? I would call that a partial. And so then I would multiply the partial by the run, the dx, and I would just be left with that vertical change. So I'm going to call this f sub x. And if I also multiply this by delta x, I would get my vertical change along the one side. And how about this? I'll do the same thing with b. Y, j, plus again, this is going to have a y-ward slope. How much does it slope? Well, it depends on the change in y. Well, we're calling the change in y delta y, so this will just leave me with dz. This just leaves me with dz, so I'm looking at a change in z, k, due to the change in y. Oh, I love this. Back to chain. We're like, this is good stuff. Okay, I have these two. Well, if I want to know the area of this and two vectors span it, how do I find the area given two vectors? A cross product. And you're going, please, no, please, no. Absolutely, y'all. This is so good. You won't believe what happens. You seriously won't. Because when I do this cross product, negative f sub x delta x y minus f of y delta x delta y plus delta x delta y. Okay. And you go like, okay, well, I like that looks terrible and ugly. What if I did this? What if I factor out the delta x delta y? Okay. What if I took the magnitude? Because that's going to give me the area of the parallelogram. This just gives me some orthogonal vector. Let me take that magnitude. And you know what? We are going to redefine this in just a moment. So I'm going to push this guy to the side. Over here, we'll come back to it. But this would just give me partial x squared, partial y squared, plus 1. Hey, yo. And guess what? This doesn't disappear. We just call this dA, the differential of area. So now if I put it all together, to get surface area, I do a double integral over a region of this dA. Calculus is beautiful, folks. And it all comes from the fact that I can take one thing, and again, if I'm it's like I'm filling this whole thing with a bunch of parallelograms with just a bit of vertical change, and their x and y change localized, and then when I cross them and get that area, the x and y change stay localized, and then I have this kind of dz component out there, this dA component out there, that also is accounted for. Easy. Easy. I mean, this is a quickie. Now that we've established this formula, let's go. Find the surface area, the part of this surface over this triangle. So I have some kind of parabolic with a little bit of a line to it, and a triangle, and I'm just looking for that surface area. Again, it's good to sketch a region just so we see it. 0, 0, 1, 0, 1, 1. All right, I see this. When I set up this double integral, I could go either way, but let's just do this one. This one's easier. From y equals x being my roof to y equals 0 being my bottom. And from x equals 0 to x equals 1 being my left and right. Okay. So I set up those double integrals. I wanted to put my numeric one on the outside in case you forgot, and my function one on the inside. Now I'm just going to fill this thing up with my partials, and I'm going to go dy, then dx, because that's more beneficial and it matches my integral bounds. So this is going to be 2x squared. This is just going to be 2 squared. This is just going to be 1. Well, now I have this integral from 0 to 1, 0 to x of 4x squared plus 5 dy dx. And it gets even better. Guess what? This is a constant in terms of y. So this next step is just this thing times y evaluated from 0 to x. Because this whole term is just a constant in terms of y. So now I'm going to plug in that bound. 0 cancels out the other side. 0 to 1. This becomes 4x squared plus 5 times x dx. Guess what? The u sub has arrived. Just that straightforward, where u is 4x squared plus 5. du is 8x dx, so du over 8 is that stretch shrink factor, which we'll learn about in 15.9 a little bit more. I also have some bounds to move. When x is 0, u is 5. When x is 1, u is 9. And so those are my new bounds from 5 to 9. The square root of u times 1/8 du becomes 1/8 times 2/3 u to the 3/2, evaluated from 5 to 9. Just like that. This becomes 1/12? Yep, 1/12. Now we have 9 to the 3/2 minus 5 to the 3/2. The 9 to the 3/2 does get a little bit nicer because it's like 9 rad 9 and 5 rad 5. That's 1.5. That's 1.5. So the 9 rad 9 becomes a little bit nicer, but it's still kind of ugly. 27 minus 5 rad 5. Not that pretty, not that bad. Final answer. One more problem on the back. Find the surface area of this part of this paraboloid under this plane, z equals 9. Again, I know my surface area formula. And it has the same stretch and shrink factor. So from above, it's a circle. And eventually it runs into 9. Okay. I see x squared plus y squared. Let's see what happens. Let's see what happens because that like I'm seeing 9 equals x squared plus y squared. I'm very clearly seeing a circle as my upper bound. If I think of how this bowl kind of sprouts here and hits that sheet of paper, when it starts at the origin, it's just 0, 0, 0. Right? When z equals 0, x and y equals 0. But when it gets to the top and z equals 9, this thing is a radius of 3 circle. 9 equals x squared plus y squared. So I'm going to guess that a polar sub is going to come. Just because of the way the bound kind of looks. I'm not going to quite define those bounds. I could in terms of x and y, but we know anytime we have a circular region, we'd much rather become pirates. Here we go. Let's see if the integral lets us do that. My partial x is going to be 2x squared. My partial y is going to be 2y squared plus 1. And there it is. I see it. Do you see it? 4x squared plus 4y squared plus 1. Let's make the change. 4r squared plus 1. I know I need to change this to be r dr d theta. And don't run off yet, folks. We have to talk about the bounds. We have to talk about filling out those integral stabs. So up here, I see if I wanted to consider this in terms of r, x squared plus y squared equals r squared equals 0. So I have my r bounds. And it's the surface area. It's the full circle. So I need to theta all the way around this shape. 0 to 2 pi. R equals 0 to r equals 3. Of this r times 4r squared plus 1 dr d theta. Harder. That was a bad one. That was a bad one. Again, another u sub inside. Like, a u sub becomes the strongest skill we have. Du is 8r dr. And again, it's a 1/8 coming out of here. How about that? That'll make our lives a little bit easier because we've done it before. So let's see. And we have some bounds too, huh? My bounds, r equals 0 makes u equals 1. R equals 3 makes 9 to 37. Those are some nice bounds. One eighth square root u du d theta. Yep, that's it. And we're off. We already did this 1/8, 2/3 u to the 3/2, evaluated 1 to 37 d theta. That's 1/12. This is getting bad. This is getting bad. 37 rad 37 minus 1 d theta. And the good news or bad news, depending on how you want to say it, like this is just a constant. My calculator knows what this value is. So now it's just going to be 1/12 37 rad 37 minus 1 theta from 0 to 2 pi is pi over 6. 37 rad 37 minus 1. This is great. I love calculus. Come on, folks. 13 minutes. He did it in 13 minutes. No, he didn't. He did.